Hello everyone, and welcome to the Newton's Second Law Post-Lab Part 2, in which we are going to both post-lab the second part of our lab and take the two parts and put them together into one big, glorious, very important math model. So let's start out by kind of going over what you found in the second part of the lab, which was acceleration versus mass with constant force. So you kept the force constant by keeping the hanging mass the same. Right? Because remember, the net force was the force of gravity, the weight, if you will, of the hanging mass. Right? And then you change the masses by putting masses on the cart, which changed the acceleration. You then made a graph of acceleration in meters per second squared versus mass in kilograms. And when you did that, you got a graph that looked unlike any we have seen thus far this year. Right? It looked like that. That's not a parabola. That is what is called a hyperbola. And a hyperbola is indicative of a very special and new relationship that we haven't seen before. So consider, as you added mass, as you made your mass bigger, put more and more mass on the cart, what happened to the acceleration? Yeah, it got smaller and smaller. Mass got big, acceleration got small. You can go vice versa too. Mass gets small, acceleration gets bigger. Well, what kind of a relationship is that? What do you call a relationship where one variable gets big and the other gets small? And that's called an inverse relationship. And so hopefully when you went to linearize, you didn't square or square root, you inverted the mass. You graphed the acceleration in meters per second squared versus 1 over mass in 1 over kilograms. Notice you have to invert the units as well. And if you did that, you then got a linearized graph. You got a linear graph that contained 0, 0. Or at least it had a small enough y-intercept that we could neglect it. And what do we know about two variables, or the relationship between two variables, when they result in a linear graph that goes through 0, 0? Yeah, those two variables are said to be proportional. But not acceleration and mass. That didn't give you a linear graph that went through 0, 0. It's acceleration and 1 over mass that are proportional. And in fact, there's two different ways to say this. Okay, you could just read it. The acceleration is proportional to 1 over the mass. Okay? Or you could use the magic word. You could say the acceleration is inversely proportional to mass. The acceleration is inversely proportional to the mass. Notice you don't say inverse and 1 over mass. It's like a double negative and it would cancel itself out. So you either say acceleration is proportional to 1 over mass, basically read the symbols, or acceleration is inversely proportional to the mass. Now let's talk about what that means, okay, at least from a proportional thinking kind of standpoint. So if we double the mass, what's going to happen to the acceleration? Well, remember here, as the mass gets bigger, the acceleration got smaller. So if we double the mass, the acceleration will get smaller, but by what factor, since it's an inverse relationship? By 1 over 2, or 1/2 as much of an acceleration. If we triple the mass, the acceleration will now be 1/3 the original acceleration. See how that works? You got to inverse it, right? You got to invert it. Fun with fractions. What if we cut the mass in half? So instead of having a big mass, we had half the mass. Now notice that means the acceleration will get bigger by a factor of, well, what's 1 over 1/2? 2. Right? So the acceleration will double. 2 times as big. See how that works? I got to do a little fun with fractions and inverting in this relationship. And in this relationship we found we kept the force constant. Okay? And what force we used will factor into how we deal with this in just a few minutes. So now that we understand the basic relationship, an inverse relationship, right? We can build a math model not out of the original graph, because it's not linear, but out of our linearized graph, using, of course, y equals mx plus b. So the y variable here, what we graph on the y-axis, is the acceleration. It's going to equal your slope. So let's take a look at what we got for slopes in this half of the lab. You'll notice they're all pretty close to one another. Some are a little bit less than 1, some are a little bit more than 1. And as we go down, we can see an average slope here of about 1.004, which is pretty darn close to 2 sig figs to 1. Right? Was yours pretty close to 1? I'm guessing it probably is, right? If you did everything right, it looks like we get pretty much slopes of really near 1. So, if we plug a 1 in, right, for our slope, then we need to talk about units. Right? Now the units for a slope, just like when you find a slope, you find from rise over run. These are pretty complex looking units. The units of rise are acceleration units, meters per second squared, and the units of run are inverted mass units, or 1 over kilograms. Now that looks really hard to interpret, but let's take a minute to simplify these units if we can. What does this horizontal line mean? It means to divide. So this is a meter per second squared divided by 1 over a kilogram. Well, remember your fractions. Dividing by 1 over a kilogram is the same as multiplying by the reciprocal. It's the same as multiplying by a kilogram over 1. And once you do that, you get a kilogram meter per second squared. Uh-oh, I hope some bells are going off here, right? What's a kilogram meter per second squared? Well, in our definition of a Newton lab, we found that that's, in fact, the definition of a Newton. So a kilogram meter per second squared is a Newton. So actually, this whole big mess of units here reduces down to a Newton, a unit of force. So perhaps this has something to do with the force acting on our system. We shall see as we work. With me there? Okay. So now the next step is, what is the x variable? Oh, I think before this, let's talk a little bit about sources of error. If you want to do a percent error calculation to see how close you were to my 1.0, of course you should round yours off to 2 sig figs, which is going to take care of a lot of error for some people. Same 2 sources of error that we had in part 1. You might have a slightly different system mass than I did, depending on your cart and your masses. All right, they're not identical. They're pretty close, within a few grams. But the bigger reason, probably most of the error that you see, is how good of a job I did in balancing friction with the angle of the track so that we could ignore them, right? If I overbalanced or underbalanced a little, that's going to change your accelerations, right? Because it changes your force slightly. And so it's how well I balance this. But it looks like with our data that I must have done a pretty decent job, because it's, pretty well, everybody got pretty close to 1. So again, the x variable is what we graph on the horizontal axis, and that's 1 over the mass, not mass. That's not your linear graph. That's your 1 over mass, which gives you the hyperbola if you use the equation. That's why this equation describes that graph. And the y-intercept here, well, it's 0 here. But this is the other little quirk of understanding an inverse relationship. There isn't a 0, 0 on the original graph. So it doesn't mean when the mass is 0, the acceleration is 0. In fact, when the mass is getting smaller, the acceleration keeps getting bigger and bigger. So we need to use a little calculus-y limiting kind of idea here. So I'm going to help you with this so that you understand what this is when you see it again. So I want to make 1 over mass approach 0. Well, if 1 over the mass is going to approach 0, what kind of mass do we need? It's on the bottom of the fraction. It's on the denominator. So we need a really, really big mass, right? 1 over a really, really big number is really small. What's a really, really big number? Infinity. Right? It's a really big number. So what this y-intercept means, the reason that it's negligible, is because as the mass approaches infinity, the acceleration approaches 0. Okay, this little arrow means approaches. It's a little pre-calculus notation. As the mass approaches infinity, the acceleration approaches 0. And you could really reverse that. You could say as the mass approaches 0, the acceleration approaches infinity. Seems kind of weird, right? But if you kept piling masses on the cart, kept piling masses on the cart, kept piling masses on the cart, right, it's going to slow down, slow down, slow down, slow down. Right? So again, a little weird here with the whole inverse thing for the y-intercept. But since it ends up being 0 in our linearized graph, right, we don't have to add a 0, and this becomes our second math model. And in this half of the lab, where we varied the mass and measured the acceleration, we kept the force constant. You all had a hanging mass of about 0.105 kilograms, 105 grams. If you multiply that by 9.8 newtons per kilogram, you get a constant force of about 1.03 newtons, which is to 2 sig figs, 1.0 newtons. Don't worry, it's not a coincidence. We'll figure this out in just a moment. So, after doing both parts of the lab, right, with our 3 variables, acceleration, force, and mass, we found 2 things. Right? We know that the acceleration is proportional to the force when the mass is constant, and we know the acceleration is inversely proportional to the mass when the force is constant. Would you remember what we did with this when we did the area of a triangle lab? When we had a situation like this, we took the 2 variables and we multiplied them together. We said the acceleration is proportional to the force times 1 over the mass. Didn't add them, didn't divide them, didn't subtract them. We have to multiply them. Why do we have to multiply them? Well, because that's the only way you hold the original relationships. If you just double the force, this ratio will still be twice as big. If you double the mass and leave the force alone, right, this ratio would be half as big. So we hold the original relationships, but it also allows us to see what happens if you change both. What if we double the force and we double the mass? Well, in the fraction, it's easy to see that those just cancel out, right? If you double the force, you'd double the acceleration, but if you double the mass, you'd have the acceleration, and 2 times 1/2 is 1, right? So this shows us that our acceleration just wouldn't change. Our new acceleration would be our old acceleration, right? And we did this, if this is freaking you out a bit, we did this back in the area lab to come up with 1/2 base times height, right? For the area of a triangle, we multiplied the base and the height together. So this is something you're going to see a couple other times this year as we go throughout the year, whenever we do these multivariable labs. Okay, so this is better, and surely there is some good concept builders along the way here where you will do proportional thinking. What if I double this and quadruple that? What if this is half as big and the other one doesn't change, right? And figure out what'll happen to the acceleration. But it doesn't allow us to do the more powerful, this much force acting on this much mass is this much acceleration. For that, we need an equation. And to turn a proportionality into an equation, we need to throw in what we call a constant of proportionality. Right? That's little z here, just a dummy variable till we know the number. This is the definition that I gave you just like back in the area of a triangle lab. Now, if you remember or you think back to that one, we ended up figuring out that the constant of proportionality was 1/2. Therefore, the area of a triangle was 1/2 base times height. We did that by comparing our general math model with our as yet unknown constant z to the 2 math models we got out of part 1 and part 2 of the lab. Right? And those 2 led us to values of z, in that case, was 1/2 with no units. Okay? Let's see what it is in this lab. So let's take the result of the first half of the lab. Right? The acceleration was roughly 1.31 over kilograms times the force, and in this case we kept the mass constant at about 0.777 kilograms. And then here is our general math model. Well, let's compare these 2 equations, right? We want both of these equations to be accurate descriptions of the reality of our modified Atwood's machine. So what does z have to be to make both of these equations work? Well, since these are all multiplied together, right, multiplication and division, I can use associative and commutative properties to rewrite this. So I'm going to rewrite it to look kind of like the original equation we got out of the first half of the lab. Everybody okay with my algebra here? Really, I just pulled the force out here and left the other parts. Okay. But look what we have now. Compare these equations. Both of them have the same y variable, the acceleration. Both of them have the same x variable, the force. Both of them have 0 y-intercepts. So the only way our general equation can match our experimental equation we got from the first half of the lab is if the slope we got in the first half of the lab is theoretically z times 1 over the mass. See what I'm saying? Just comparing these. This part's got to be the same for these two equations, right, to both be accurate, to both describe what really happened with our modified Atwood's machine. Well, note here that this has 1 over the mass. And in this part of the lab, we kept the mass constant. We know what that constant mass is. And please use yours, right, whatever yours was, if yours wasn't exactly like mine, right, and that'll help you match what you got. So let's see what 1 over that constant mass is. In my case, that's 1 over 0.777 kilograms to 2 sig figs. You know what that is? That's 1.3, 1 over kilogram. Well, look, that is the slope we got in the original part of the lab. So if 1 over the mass is 1.3, 1 over kilograms, and our slope is 1.3, 1 over kilograms, then what does z need to be? Well, if we're going to multiply by z, we're going to go z times 1.3, and we want to get 1.3. I'm not trying to be difficult here. Yep, z needs to be 1. And z doesn't even need any units, because 1 over the mass has the same units as our slope does, at least once we reduce them in the post-lab. This is, as you're going to see, is the world's best constant of proportionality. And you'll see why in just a couple minutes here, okay? But it's 1 with no intercept, or sorry, with no units. So if we plug a 1 in here, and we take 1 over our constant mass, we get the slope that we actually found in the lab. So let's see if this works in the second part of the lab. All right, we got a relationship like this just earlier in this video. The acceleration is 1.0 newtons when we reduce the units times 1 over the mass. In this part, we kept the force constant. 1 over was 1.0 newtons. Our general math model still, the acceleration equals our constant z times the force times 1 over the mass. Let me rewrite it to look more like this. And do you see it again? All right. The slope we got in the lab has got to be z times the force. But in this part of the lab, we kept the force constant at 1 newton, which is exactly what the slope was. So again, what does z need to be? 1, right? With no units. If you take 1 times 1 newton, you get 1 newton. This kind of thing is in fact what I was doing to check your slopes. It's how I knew how to set up the Google form to tell you whether your slope was accurate or not, right? I knew what we were going to get out, and I knew how to pull the slope out of our general math model. Tricky, eh? It's using math. So if we go here, and here's our general math model, but we now know that z is 1 with no units. If we plug that in, right, well, multiplying by 1, doesn't do anything. It's the multiplicative identity. So we get the acceleration is the net force over the mass, or you could say the acceleration is the ratio of the net force and the mass. Okay? That's in fact kind of how Newton wrote it. Right? He actually didn't use acceleration, but it's close to the way he wrote it originally. All right? And this is kind of nice. Right? It allows us to say if you apply a certain amount of force to a certain amount of mass, you'll get a certain amount of acceleration. Or with, of course, a little algebra, we could solve for any one of them. Typically, it's not written this way. It's solved for the force. I don't know why. It's just the way you would see it if you look it up on the, Concept Builder Guy's website. So if we solve this for force, we have to multiply by m to move it to the other side. And we get what we are going to call Newton's second law of motion. The net force is equal to the mass times the acceleration. And this acceleration is, in fact, the acceleration we saw in the kinematic equations. Hint, hint, nudge, nudge, right? Eventually, we're going to use those in this unit. If you have a constant amount of force, you get a constant amount of acceleration, as we saw over and over and over in these two labs that we did, that we put together here, right? The forces were constant, and so the acceleration was constant once you let the cart go. Notice, though, that this is the net force. It's the unbalanced part of the force, if you will, right, that causes it to accelerate. If the net force is 0, well, then the acceleration is 0, Newton's first law. This law is super important, okay? Without understanding this law, it is really hard to understand why things move the way they move. Okay, this is the law that governs all of it here. This Newton's So we are actually going to spend the rest of the unit going over this equation and applying it to more and more and more complex situations. And that's where the math is going to get a little hefty. But we're going to start out by doing some concept builders and some other things to try to get the relationships sorted out in your head. So I hope you've enjoyed this big, long, several-day Newton's second law lab.